Hi, Mehdi. Welcome, Professor Jia. Welcome, Abder.
Hi, John.
Good morning.
Hi, good morning.
Hey, Chen, is it possible for me to do a quick test on screen sharing? I just want to make sure.
Oh, yes, sure.
Okay, so, okay, just a second.
I can, I think I should.
Yeah, if you quit, and then I can just do a quick test. Okay. Has it started yet? Okay. Nothing there yet. Yeah, it says that the host disabled participant screen sharing. So I think it's fine as long as you enable that.
Could you please try again?
Yeah, sure. I'll try that. Okay, I see that thing. All right, it's supposed to work, I think. Can you see it now, or I guess I?
Yes.
Okay, cool. So I'll quit. Just want to test that, or maybe the video. Let me test the video quickly. All right. All right, so I quit. Thank you.
Yeah, thank you very much. Welcome, Alex. Good morning, everyone. My name is Yuchuan. Today, it is my greatest pleasure to host all of you here with my supervisor, Professor Abdullah Rahman Kadar. The name of the workshop is High Dynamic Motion Generation for Under-Actuated Robots. Congratulations that you have made the right choice for many, many interesting topics today. Basically, our objective is to make robots faster, but sometimes not too fast. Otherwise, it could be problematic. Please let me recall some fading examples back in the DARPA Robotics Challenge in 2015. The state-of-the-art humanoid robots cannot handle high dynamic motion or dynamic contact transition robustly. We believe that our speakers today can address this issue from the following aspect. For detecting the impact of collision between the robot and impact and the environment, Patrick Wensing is going to share his experience. And Yan Bin is going to present his recent achievement with the frictional impact dynamics using a batting object example. The state estimation for floating-based robots is important for control and difficult to handle. Mehdi is going to talk about it. The humanoid robots is fragile in many aspects, the fragile motors and the harmonics. Zeyu and Patrick are going to cover the hardware aspects. The dynamic balancing will be touched by Professor Nanchiv and Roy Featherstone, and also myself. And all of us are going to focus on the high dynamic motion generation from the control perspectives. So today's agenda is here, and our first talk will go to Patrick Wensing from University of Notre Dame. The topic is It All Matters, Considerations Across Design and Control for Contact-Savvy Robots. Patrick, could you hear me, please?
Yeah. Thank you, Johan. I'm going to try to share my screen here. Let's see here, desktop one.
Okay.
Can you all see this all right?
Yes.
Okay, let me get you over here. All right, excellent. Well, thank you so much, Johan, for the invitation. It's great to see so many friendly faces here, if only virtually. I hope maybe next time when we get together, it'll all be behind us and we'll be in person. So I'm excited to talk about some considerations across design and control for contact-savvy robots. Johan had asked me specifically to talk about some of the design stuff that I'll be speaking on from some of my postdoc work, and then transitioning to some of the work I've been doing at Notre Dame. So one of the benefits of being on Eastern Standard Time is that I get to go first. The other benefit is that if you all disagree with what I say for the rest of the day, it won't hurt my feelings, because I'll have to go to sleep here sometime soon. So I'm sad I'll be missing some of the talks, but looking forward to catching them on YouTube, hopefully later. So before I jump into my my topic for today, I'd just like to plug some of the work that I'm doing kind of more broadly in my lab, the Robotics Optimization and Assisted Mobility Lab, or ROAM lab, at the University of Notre Dame. And so work in my lab is focused on advancing mobility for legged robots broadly defined, both quadrupeds and humanoid robots. And we're looking to advance these technologies so that legged robots can go anywhere on land, And we're looking to translate those technologies into assistive devices so that people can go anywhere on land, even after they've had an injury that might otherwise limit their mobility. So we're looking at problems in exoskeleton intent detection and looking at translating some of our reduced order control designs from bipeds and quadrupeds over to the prosthetics side. So, I'll be mostly focusing on this left-hand side today, but I hope down the road we might be able to talk about some of these applications on the right-hand side and some discussions together. Okay, so turning to our matter at hand, let's talk about contact-savvy robots. So I'd like to show here a video of Cheetah 3 handling this set of stairs blindly. So Cheetah doesn't know here that these stairs are in front of it. Instead, it's using some proprioceptive actuator technology that I'll be telling you about in order to essentially feel that it's touching down, and then to adjust its model predictive controller in order to recover balance for the torso. And so as Yuan had motivated, I think this ability to manage dynamic contact transitions, detect impacts is really a fundamental importance as we look to send robots beyond the lab. So whether it's a robot that's supporting our troops or going into a disaster zone, the scene of a fire, or into our homes, these systems are going to bump into objects and people that they didn't anticipate. And so this ability to kind of gracefully handle unexpected contacts and unexpected physical interactions in particular is quite important. And so the main thesis of my talk today is that essentially this problem, even though we often think about controlling these interactions from a control side, that it really is a coupled problem across both design and control. And I see a lot of motivation for that from biology and seeing how animals in nature handle unexpected physical interactions. So to motivate this is one of my favorite videos. This is from Bob Full at Berkeley. So he had this cockroach run across this gel surface, and they were able to measure the forces under the feet. And here, as this cockroach runs along, the unexpected physical interaction is that there's actually a little tiny cannon that's mounted on the back of the cockroach that's going to apply a disturbance force to the body. And so the kind of beautiful thing that they found when analyzing the ground force data following this disturbance was that the forces that were under the feet of the cockroach were, one, stabilizing to help recover its posture, and two, they occurred faster than could have possibly happened through closed loop neural feedback. But that's to say that there's something with the body of the cockroach that had passive dynamics engineered correctly to help reject this disturbance. And so I think in terms of managing unexpected contacts, it's really a combination of kind of brain and body. Here we see the body side, but of course, as we go into more challenging environments, there is a cognitive aspect, and there's no denying that. So here for this baby ibex, the dynamics of its muscles and tendons and ligaments are providing some passive dynamics that help to make its motion efficient, but there's definitely a cognitive aspect in terms of planning its motions. So, as we look to send our robots into these types of situations, I'd like us to think both about the design side, the control side, and really how these two come together to make our system perform at its highest levels. So in terms of where I'll be going today, I'm going to first talk about some of the actuator paradigm that I've been using in my research, these proprioceptive actuators. And I'll acknowledge this is really the brainchild of Songbei Kim from almost 10 years ago at this point. And so much of the credit for the original idea, all the credit for the original idea goes to him. So we'll take a look at that and look at why I think these actuators are ones that we should consider integrating into our robots that are undergoing contacts. And then we'll take a look at some of the motion generation aspects with a mini cheetah robot that I have done in my lab, some new strategies for trajectory optimization with hybrid systems. This is some work with my student, Li. Then after we've talked about design and some of these control aspects, I'd like to talk about some more preliminary work that's going on in my lab, where we're trying to design robots that are easier to control by trying to formalize how we can engineer passive dynamics by looking at design and control together. And this is some work that's in collaboration with my student, Gabriel Bravo and Andrea Delpret. So let me first jump into this actuator analysis part. So here's an early video of one of the proprioceptive actuators, the first one that Sangbei built actually before I was in his lab as a postdoc. And as I said, I think these, when this video came out, it was very shocking. I think Sangbei had said people at DLR were just, blown away that it wasn't breaking the gearboxes, right? And so, I think this type of actuation paradigm is really well suited for managing unplanned contacts and for helping our systems move in a highly dynamic manner through the world. These actuators enable us to have high bandwidth physical interaction through contact. They help us to mitigate impact impulses by being highly transparent, and they have a pretty high torque density. So for every gram of actuator we carry along, we get a bit of torque out of it. In terms of key features here, these proprioceptive actuators, or also known as quasi-direct drive motors, have a high gap radius stator and a low gear transmission. And this strategy of essentially minimizing the transmissions and the transmission dynamics allows accurate delivery of force without external force sensors. So I'm saying here accurate force delivery to mean that we can get forces down to the foot in an accurate way. And I'm going to contrast that with force control, where force control would be something where you take feedback from a force sensor. So we do kind of, in a sense, have co-located force control here, that we have a current monitor on the motor, and so we can use that to get torque control on the motor side as opposed to at the output. And there's no springs or stiffness modulating mechanisms in this type of a design. You can kind of think of these proprioceptive actuators as phantom robots on steroids. So in these phantom robots for surgical tasks, the goal is to render impedances at the endpoint as accurately as possible so that the surgeons can feel, mock tissues. And so it's really just a scaled up version of that. So how does this compare to other actuation paradigms? Well, let's consider perhaps the most common one, where we've got a motor and a high gear ratio transmission and a stiff torque sensor, and then our high inertia leg. So here, you can do feedback control on the stiff torque sensor, and empirically, we've seen, closed loop force bandwidths 5, I would say probably in more of the recent DLR hardware, probably up closer to 30 in some of them. But these designs are kind of fundamentally not impact robust. That if I were to use a hammer and bang on the end of the leg, there'd be a very large force ripple that would go back through this chain and often excite unintended structural vibrations that really complicate control. So in order to address that, of course, many folks have looked at series elastic actuators, adding a spring in series there in place of a stiff torque sensor. And by closing a position loop on the deflection of this spring, you can control the torques that are delivered to the leg. I would say 15 up to 30 or 45 hertz, actually, in some of the more recent ones with out of Luis Sentis's lab and the like. So here you get a lot of impact robustness, but you do have to fight this spring. By comparison with these proprioceptive actuators, by really minimizing the transmissions, we get a very high delivery bandwidth of forces, empirically observed up around 100 hertz. And by minimizing the reflected inertia, these designs are quite robust to impacts. So I'd like to take a look a little bit more formally as to why this design performs well. So let's consider a simple leg model. Let's imagine that we have a main body here with mass MB, and a leg mass over here with mass ML, and a rotor with an inertia I. And we'll denote the angle of that rotor with theta. So we're going to imagine this leg interfacing with the ground with a stiffness Ki. And let's consider what happens if I put a torque essentially onto this rotor. How does that map to forces at the feet? Right? Of course, there's some springs in here, so it's not an immediate mapping, but we can look at the transfer function from the torques at this motor to the forces at the ground. And if we do that, you can see that the bandwidth for the delivery of forces, kind of intuitively, here I'm graphing leg mass on this axis, inertia on this axis. Yellow is higher bandwidth. So we maximize bandwidth by minimizing leg mass and inertia. In a similar vein, if we take this system and we pull it up in the air and we drop it down and we look at the maximum force that we see during an impact, in that case, blue here is lower, so low leg mass, low inertia leads to the lowest impact forces. So from this simple analysis, low leg mass and actuator inertia maximize bandwidth and minimize impact forces. So how does this compare, however, when we add a series elastic element in here? So let's put an elastic element Ks in there with stiffness Ks. And now if I look at the open loop mechanical bandwidth from torque at my actuator to force at my foot, I actually have two poles in my transfer function, one graphed here in red, one graphed here in blue, graphing the frequency of the poles in my transfer function as a function of my spring constant here. And so over on the right, you can think the cheetah is essentially a rigid transmission, and this predicts when we add realistic values for the different parameters here, it predicts that cheetah would have a open loop force delivery bandwidth of around 80 hertz, which is roughly what we see. If you put in a series spring stiffness of 70 Newton meters per radian, which is from one of the earlier versions of Animal from their Starleth robot, it predicts a closed loop bandwidth of around, or an open loop control bandwidth of around 13.5 hertz. And so the point I want to emphasize here is that this is really open loop bandwidth. But if you want to do something that's faster than this with an SEA, you can, but it often takes a lot of control effort. And in practice, we see that the bandwidth for these SEA robots as kind of roughly similar around here. And so the overall observation is that due to actuator limitations, mechanical bandwidth, this open loop force delivery bandwidth, ultimately limits force control bandwidth when you incorporate feedback. So we've quantified these bandwidth numbers, but I haven't really quantified this impact robustness. So we in our paper in 2017, we came up with a way to kind of quantify the capability of the passive dynamics to mitigate impact impulses. Let me try to diagram it for you. So we've got our equations of motion for the robot, and we know that when the robot flies through the air, when its foot hits the ground, there's going to be an impact impulse that's kind of opposite to the impact velocity. And it turns out that impact impulse is scaled by this matrix lambda that's the operational space inertia matrix. It's essentially the effective mass that you would feel at the foot if you were to probe it right before it touched the ground. So we wanted to look at, this clearly plays a role in the impacts we see. How can we compare this across robots of different sizes? How can we non-dimensionalize it? So our idea was to take these equations of motion and partition them down into the floating base and these joint components. And then ask the question, what mass do I have at the foot in the worst case? And the worst case might be when all of my joints are rigidly locked and I just hit like a rock at my foot. If all the joints are locked, then essentially these J components just go away in a sense. And you're left with this worst case locked inertia. Now you can think this locked inertia, it's got to be worse or larger than the regular contact inertia, and you can prove that that's the case. And the implication of that is that this following quantity, this determinant of identity minus lambda times this locked inertia inverse, that this determinant is between 0 and 1. And let me give you some insight into it. In the best case scenario, when lambda is 0, if there's no contact mass and so no impact impulse, when lambda is 0, then I have the determinant of the identity, so I get a 1. So 1 is good, best case scenario. Worst case scenario, if this matrix lambda is equal to the locked case, then I get an identity matrix when I do this multiplication. So I get the determinant of 0, I get 0, which is bad, right? So 0 is bad, 1 is good. So we took a look at these numbers for a couple different actuation paradigms. Here we looked at Hubo first. I'll note that this impact mitigation factor does depend on your knee angle. You know, you can think if your leg is outstretched, if you're closer to singularity, that gives you less ability to kind of absorb the impact than if you have a bent knee. Right? So here's Hubo and here's Cheetah via comparison. So we can see, you know, in the most reasonable part of the workspace, Cheetah is drastically outperforming Hubo. So this shows kind of a more conventional paradigm versus the proprioceptive, but what about those series elastics? So if we graph the series elastics, they do outperform Cheetah a little bit in terms of this impact mitigation, but I'll remind you that, you know, in terms of adding that spring, you're often either adding a lot of complexity in the controller and sacrificing some bandwidth for your force control. So in terms of what this buys you for during control, we did a couple of experiments. This was when I ran down in the lab. So here we had Cheetah run over this load cell that's embedded in the ground. And over here, I'm graphing time on the x-axis, force on the vertical axis, and I'm showing the lateral and vertical force here. And in blue is a desired force from a balance controller. And in red is the force that we're measuring from that load cell. And I'll emphasize here, the robot doesn't have feedback from the load cell. It doesn't have any feedback, you know, it doesn't have a load cell under its feet either. This is just open force delivery. And it's, you know, it looks reasonably accurate, but I think the more impressive thing here in terms of being highly dynamic is that we're looking at, you know, from 0 to 500 newtons in 40 milliseconds and then back, right? And to put that in context, right, like the blink of an eye is around 300 milliseconds. So these are just fast dynamics. So what are the benefits of these proprioceptive actuators? They allow you to mitigate impacts. They allow you to deliver forces quite well. The other thing that we found is actually a nice implication for system identification. And that's that these actuators, by minimizing kind of the parasitics in the transmission, actually make our rigid body assumption much better than in other cases when it might be. So we did a test where we tried to identify the Cheetah leg. We slung it around on the table and gathered some measurements for the joint angles and joint rates and the torques at the joints. And then we attempted to identify some of the mass inertial parameters given by pi here, where y is the classical regressor matrix. So we're trying to fit some data and also trying to not stray too far from CAD data here with pi hat. So when you do this, even though you get a somewhat reasonable model, the mass distributions that you get out are just, you know, absolutely horrendous. So here on the right is are showing the kind of equidensity contours for the identified mass distributions coming out of this this identification. And we found this was some work from me, Sangbei, and Jean-Jacques Slotine in 2018, and then followed up in collaboration with Tae-Yoon Lee and Frank Park. Really, the culprit here is this Euclidean regularizer. And we found that we can essentially take that, drop it out, and put instead a new regularizer that's also convex, that has this nice connection to entropy and the KL divergence. If I give you two inertia matrices, I can calculate this quantity, and it's invariant to reference frames and physical units, and so is more sensible than the conventional Euclidean metric, which is dependent on choice of frames. And so with just this very small change, we can get much more sensible results out of our system identification. I think it's really easy to mess up system identification sometimes, and this makes it harder to mess it up. In addition to identifying mass distributions that are reasonable, we also get a really good model out of this. So here I'm showing you the abad and hip angles on the top, and then down here in blue is the measured torque coming out of the motor amplifier, or the predicted torque coming out of the motor amplifier, and in red is the model that we've identified. So essentially we can do inverse dynamics down to about a Newton meter RMS, where a lot of that's just coming from the noise here. Okay, so big picture takeaways. I think when it comes to managing physical interaction and having highly dynamic robots, these proprioceptive actuators have a lot of benefits. They enable high bandwidth delivery of forces, minimize impact loading due to reduced reflected inertia, and this actuator transparency really enables accurate rigid body modeling. Okay. So I'd like to shift gears now and take a look at some of the work we've been doing for optimizing trajectories with these systems that have impacts. In my lab, we've been really encouraged by some of the work that's going on in many labs in Europe and elsewhere that's using differential dynamic programming. And so we've been looking at that as well. I'd like to give a brief introduction to DDP here first for those that might not have seen it before. So in its most simple form, DDP solves an optimal control problem that's given in discrete time form. So here we've got some running cost and some terminal cost and our discrete time dynamics. And the idea with DDP is that we'd like to be able to find the value function, or the so-called optimal cost to go. And to do that, we'd have to solve Bellman's equation, but we know that we can't do that because of the curse of dimensionality. So the idea in DDP is to instead consider some nominal trajectory and then consider some small change in state and control around it. And so if I take that right-hand side of the equation and I expand it out to second order, I can find a rule that tells me how I should update my controls based on how far my state is away from the nominal trajectory. As a kind of a technical detail, these two quantities, kappa and k, depend on the Hessian and the gradient of the optimal cost to go at the next time step. And essentially by taking this feedback law and plugging it back in, you can come up with a difference equation that relates an approximation of this optimal cost to go at time step j+1 to an approximation of it at the previous time step. So this explains the name, differential dynamic programming. It's just, rather than solving dynamic programming everywhere, it's just looking differentially around a nominal trajectory. And so we can use that to improve the trajectory and repeat this process until we arrive at something optimal. In its most vanilla form or nascent form, this DDP algorithm only handles these dynamics constraints. We don't handle any more general constraints. And so that limits the ability to apply this algorithm to hybrid systems, as we would like in our legged locomotion work. So we've recently extended this DDP paradigm in order to be able to solve hybrid systems trajectory optimization problems. We consider a problem where the mode sequence is fixed. So I am now looking at some cost functions within each of a number of different modes, and I'm indexing modes by I. We've got different dynamics within each mode. And optionally, if you think for our legged robots, we might have a flight period, and then we come in contact with the ground and there's an impact. So we include a reset map that is triggered at the end of each segment, setting the initial condition for the next one. These resets just can't happen anywhere. We need to switch to stance when our foot hits the ground. So we need to include a switching constraint in this problem. And maybe there are other constraints like torque limits and that kind of thing that we want to think about too. So what our strategy does is we leverage DDP to handle this innermost loop. And we have a slight extension of it that handles this reset map to provide some impact awareness to our trajectory optimization. And then we address these other constraints via an outer loop. So we've already talked about this yellow part. Let me kind of work my way out through the rest of it. In terms of our impact-aware DDP strategy, let's imagine that I've got some continuous dynamics here. We might imagine Fi as some flight dynamics. Then we've got our reset map, and then some stance dynamics. So we know that during each of these continuous phases, we can use the strategy from before in order to understand how the optimal cost to go evolves through time. But the question is, how do we address this impact event? How do we relate the cost to go after impact with the cost to go before the impact? So we can write out what that cost to go must be in its full generality. And then through a little bit of calculus, we can expand these sides to second order, and we get a nice update equation that tells us how to update the Hessian and the gradient of this optimal cost to go on one side of the impact event to the Hessian and the gradient on the other side. Where here, this matrix J is the Jacobian of the reset map across here. And so here, what we're essentially solving is we're fixing the timing of these modes, and we're going to switch to stance no matter where we're at the end of the flight period. And so that introduces some inconsistency that we need to take care of. The way that we take care of that is through an outer loop that uses an augmented Lagrangian strategy. So here on this graph, I'm showing DDP iterations on this x-axis. On the left, I'm showing the cost of the trajectory, and on the right, the constraint violation. So we see here at the beginning, we have some constraint violation in terms of the system not switching when it's at the ground. We update the Lagrange multipliers, we get a little bit better, and get a little bit better yet after we switch them a third time. So in terms of what this looks like, here's the final solution. The final solution is a hybrid feasible trajectory. At the beginning, we have a heuristic controller that switches from flight to stance at a predefined time. And so it violates that switching constraint that I'm showing here in red. We have this impact aware step that understands how cost information before and after impact is related, but still we haven't addressed the fact that that contact needs to happen at the ground. And so it's only when we incorporate these augmented Lagrangian updates that we satisfy these constraints and we have a hybrid feasible trajectory. So we've been looking at using this in my lab to enable the mini cheetah robot that we have and to handle more challenging scenarios. So here's a video from one of our simulations doing some real-time MPC in the sim. And so you'll see here what we're doing is we're solving this trajectory optimization problem in a receding horizon fashion, always updating it as we go. And so here, this green area is an area not to step. You might think of it, green is like a garden that you don't want to step on or something of the sort. So we took these trajectories from our simulation, and we looked at doing sim to real transfer with them using the same DDP gains in our hardware, and we had some really good luck. So here's an initial video with the cheetah. Again, the cheetah's mini cheetah is not allowed to step on this area. And we get really good sim to real transfer. This is, after only a couple hours of testing. So I just want to give a shout out to Naver Labs and the MIT Biomimetic Robotics Lab for loaning us the mini cheetah. It's really a wonderful platform. We're seeing them get dispersed a little bit more broadly. Okay, so in terms of main takeaways here, we have this trajectory optimization approach that extends DDP to hybrid systems. DDP is a really fast optimizer, and now we can use it in a more broader class of systems. And when we apply our trajectories on this system that has these proprioceptive actuators, they're easy to model because the transmissions are quite transparent. It really simplifies our sim to real transfer. Okay, so we're working on doing real-time MPC right now, and we're getting pretty close. And so I hope maybe next time I'll have that to show you all. Okay, so we've looked at our actuator design decisions, our control decisions. For this last part, I'd like to kind of switch gears into something that's a little bit more preliminary, where we're looking at trying to design robots that are easier to control. And we're trying to do that by thinking about the design and the control problem together as one coupled control problem. If you have a Cassie robot versus an Atlas humanoid, you might adopt different control strategies. And so there's clearly some coupling between these types of problems, and we'd like to formalize how to address some of that. And so to motivate it, I'd like to play this old video from Steve Collins, where he has this passive dynamic walker. And so here, through really phenomenal, meticulous engineering, he's engineered the passive dynamics of this machine quite carefully so that it can walk very efficiently. So in this nominal scenario that it's designed for, this robot is highly efficient. The other thing with these passive dynamics, in addition to it being efficient, there's also kind of a closed loop control aspect to some of these designs, in a sense that if you get the design right, then if there's small imperfections in the floor as it's walking, then the system is kind of passively stabilized by its design. So when I'm thinking about designing passive dynamics, there's these two aspects that I want to capture: efficiency, and also that if there are these perturbations, the passive dynamics help stabilize me, like with the cockroach at the beginning. So clearly, these passive dynamic walkers are great. They're super efficient, but they're not all that useful in terms of where we can deploy them. So, we'd like to kind of get the best of both worlds and push these systems toward a case where they're much more efficient and much more versatile. And, thinking about design is quite heuristic, and it's really tough because there's so many things to consider. So of course here, these two axes are probably pretty limiting. I've already mentioned kind of robustness, but you might think of other axes in terms of cost and the like. So I'll just acknowledge that our current strategy of quantifying a design does have some inherent limitations, but I think can still help push us toward that goal. So in terms of what we've been doing to address this design problem, we've been trying to use some of our tools from trajectory optimization. So traditionally, now, before we were looking in discrete time, now I'm looking in continuous time. If you wanted to solve an optimal control problem, you'd have some cost, some dynamics constraints, maybe some path constraints, and some boundary constraints. And let's imagine, usually you're only optimizing state and control because your design is given. But you could think, we could add in some additional parameters that maybe represent link lengths and motor gear ratios. And if you change those parameters, it's going to change, it's going to change your cost. Maybe it takes more energy if you have a lower gear ratio, or it definitely affects your dynamics, right? But we can add these design variables row into the problem without much issue. So now let's think if we want to design a robot for jumping on a stair, right? If we were to do that, we might parameterize this problem by a couple of values. So maybe the height of the stair, the friction coefficient, the surface angle, and the costs and the constraints, and all the different parts of the problem would be dependent on those parameters. And so if we wanted to design a robot that could jump up one set of stairs, this would be a reasonable way to go about it. But we don't just want to jump up one set of stairs. We want robots to be able to handle multiple different types of environments. And so we've been looking at how we can use some tools from an area of nonlinear programming called stochastic programming in order to design robots that are kind of good at multiple different tasks. So we're going to optimize gear ratios and link geometry. And these things are going to be kind of what I'm going to call stage one decisions. They're things that we decide on first, and then they're fixed. After we make those decisions, we have subsequent decisions at another stage, where if the robot finds itself in a different scenario, it can use different control in each of those cases. So each of those cases is going to be parameterized by some scenarios. And our main idea here is that we don't just want to optimize the performance over one scenario. We want to optimize kind of the expected value of the performance across all of these different scenarios. So here, this P is the probability of a given scenario. And here, this gamma is just a shorthand for state and control. So if we can solve this problem, which is essentially solving multiple trajectory optimization problems at once, it's going to put design pressure so that our robot is good at doing multiple things as opposed to just one thing. So we have some preliminary results with a planar monopod here, looking at jumping onto flat ground, a stair, and a slope. And so we first optimized the design for jumping on this flat ground, and then evaluated it on this stair. And here you have that, the result in red. Here on the X is time, on the Y is the energy required. So by contrast, if we optimize the gear ratios of the robot, and we optimize them considering all of these scenarios, and then we just test it out on this stair, we find that essentially requiring it to be more versatile enables it to have a lower energy requirement in this case. If we optimize the gear ratios and the link lengths, we get something that takes less energy yet and is a little bit faster. So in terms of the co-design result, the designed robot completes the task faster and it requires less energy. I'll note here, this is a relatively simple case. If you think, you're solving multiple trajectory optimization problems at once, one of the real challenges is scalability, and that's something that we've been working on and making some great progress on. So as I motivated with the passive dynamic walkers, we don't just want passive dynamics that are energy efficient, we also want our robots to be robust. We want those passive dynamics to be stabilizing when things go wrong. And so the question I'd like to reflect on is what goes wrong sometimes when we have our legged robots? Well, one of the things that can go wrong is that we come in contact with the world at an unanticipated time. So this is a diagram from Honkai Dai and Rust Headrake that I really like. So let's imagine we've got this a limit cycle here in black, and then with this dashed blue. And if everything goes right, we touch the ground at the intended height, and we reset back onto our limit cycle. However, things can go wrong. We could touch down early and be mapped to something that's off our limit cycle, or we could touch down late and be mapped to something that's off our limit cycle as well. So you can think if you're designing a limit cycle, there could be bad limit cycles where a small change in terrain height leads to a very large spread in states post-impact. Whereas if you design a good limit cycle, you could reduce the clustering of those states even further. And so our thought was well, let's take a look and see what happens if we do co-design. And hopefully if we do co-design and we have a good design, we can further push down that area where those post-impact states live. So to do that, we pulled out our stochastic programming strategy again, where now the stage 1 decisions are some design variables, as well as a feedback controller. And we took a very similar simple strategy of just optimizing a time-varying linear feedback controller. Those are our first stage decisions. And then in our second stage of our optimization problem, we assess the behavior of our controller and our design under a suite of different disturbances. And overall here, this is kind of a single NLP via large-scale trajectory optimization that produces a single robot design that can handle all of these disturbances gracefully. So in terms of looking at that legged robotics application, on the left here, I've got a system that was, sorry, it was designed for flat ground, and then we looked at its behavior for this unexpected step and used a hybrid LQR strategy. And we compared that to this other case where we had robust co-design, optimizing the limit cycles as well as the hardware parameters. And the results were pretty exciting. Over here on the left, if you're not thinking about design when trying to create these trajectories for hopping, you get 108% increase in the cost of transport when you have a small disturbance. Whereas over here on the right, you got a larger disturbance, and because you've designed the system to kind of be robust to those cases, we only see a cost of transport increase of 5% over the nominal. In terms of looking at those post-impact states, here I'm showing you the phase portrait and the pre and post-impact states for the LQR controller. So here in blue are our pre-impact states, and in black are our post-impact states. And I'm showing you here phase portraits for the X position and velocity of the body, the Y position and velocity of the body, and the pitch and pitch rate for the body. So here we've got a good amount of spread for the LQR controller. Versus with our co-design controller, we've found a solution that really helps to cluster those post-impact states around the nominal, even when we have these terrain height disturbances. So, I recognize this is, simplified in 2D, but we're really encouraged by some of these results, and we're starting to look at how we can address that scalability piece and push this into 3D. So takeaways, here I'm looking to formalize the process of engineering passive dynamics. And we've first seen how we could use co-design for multiple scenarios to ensure that our passive dynamics are essentially versatile across those. And then we've looked at how we can think about design and control together to ensure that our design is kind of, in a sense, partially passively robust to these disturbances, and that we can soak up the rest through control. Okay, so with that, I'll mostly close this down. Hope I've made the case to you that it's not just design and it's not just control for making our robots contact savvy. We really need to think kind of across the board about these two, and I think there's some untapped opportunities by thinking about these problems together to ensure synergy in their solutions. Before I finish out, I'd just like to say that at Notre Dame, our robotics footprint is growing. We've got 2 new folks that are coming in over the next year. And so we're really excited. And if you're in our neck of the woods, we're 90 minutes east of Chicago. We'd love to show you what we have going on. So thank you all.
Thank you, Patrick. Excellent presentation. Very impressive.
Thank you.
So I'm wondering that, are there any questions from the audiences?
Patrick, I do have one. So you focus on the design, like of parameters like gear ratio and coupled with the different control policies. Would you think that modeling, like impact modeling, and then according to that, coupled with that, like impedance control, would also do a good job on, cheetah landing and jumping?
Yeah, I think that's a great point. So here, the policies that we've been looking at are like linear state feedback policies that are in joint space. There was some really nice work out of Ludovic Righetti's group presented by Bilal Hamoud earlier this week, where they were looking at optimizing impedances for uncertain terrain interactions. And so I think, yeah, that like the joint space stiff feedback gains map to task space in a often unintuitive way. So there might be, some benefit to looking at different parameterizations for that control policy. And you could certainly do that with the framework that we've proposed.
Mm-hmm. Thanks.
Thank you.
Other questions? If not, I would like to thank Patrick again for the great in-depth presentation and all details. It's really excellent job. Due to the time limit, we will switch to the next presenter.
Thank you.
Yan Bin from Ewell State University, and his topic is targeted batting of in-flight objects by a robotic arm.
Thanks, Yu-Chen and Abder, for organizing this workshop and for this opportunity to speak here in the workshop. So I actually like to talk about some of our recent work on batting, robotic batting. So our focus in the past few years has been on sophisticated robotic maneuvers, such as batting and cutting deformable objects, vegetables, meats, and fruits. So what does a sophisticated robotic maneuver require? Well, you have to be able to understand the mechanics behind as well as the geometry. And then you can do your planning, you plan the steps, manipulation steps. So that's kind of algorithmic. And also you do some kind of optimization, either optimize the energy or you want to minimize the time of manipulation to make it faster, swift and more human-like. And in order to carry this out, on the backbone of that is some control algorithms. You use position, force, hybrid impedance, admittance, all these kind of controls. But then you still need to estimate the state, which means that sometimes you have to rely on computer vision using filtering techniques. So today I like to focus on the batting task. And then as a byproduct, I'm going to look at the motion estimation of free flying objects, which is a component of that. So this represents the work with my former PhD student, Matthew Gardner, who's currently working at Boston Dynamics, and Xiao Qian, who's graduating pretty soon. So the goal is pretty simple. We want to hit an in-flight object to the target, just like, batting, baseball or tennis, table tennis or tennis ball. So this is the very fast and highly skillful move, because the flight usually lasts, half a second, and the robot has to make the planning and the reaction and actually execute the action within that time frame. And it also challenges the sensing and action because of the short time frame. And we like it because it also kind of intersects the impact dynamics and then the aerodynamics and manipulator kinematics, computer vision, state estimation, and also planning. So there are a lot of potential applications, especially to robots in bore spots. So here's the system architecture. So what happens is that, as you see this object on the left of this diagram is flying, and then it's captured by a high-speed camera at a frame rate of 150. And then, so they're sent to these frames of images are taken and sent to image processing. Those features are identified and give it to a state estimator, and then to estimate the current velocity, angular velocity, and position and orientation of the object. And that whole information is going to help, send it to two destinations. One is to dynamically estimate the drag and magnitude effects for us to model aerodynamics, and also for us to anticipate a certain time, ahead where the bat is supposed to meet the robot. So we have to use a little bit of a projectile mechanics there. So what lies in the center here is the impact dynamics, okay? So the arm has to move right away, otherwise there's no time, okay? As soon as the object takes off, the arm has to start moving and trying to anticipate a time, but that is actually changing. So the pose of the arm is dynamically changing, okay? And then it meets the robot, meets the object, okay? And then there is the, through the contact kinematics and impact dynamics, and then generates within, impact usually is 1/10 of a second, generate post-impact velocity and angular velocity, okay? And then the object now is open loop, you have no control after the bat, so the object is supposed to go to the target, okay? That is used as a task constraint. That task constraint is going to be taken back by, we have a 2-degree robotic arm, and to do the motion planning, okay? So the robot is constantly calculating and recalculating the pose and going to velocities at the moment of batting, okay? Based on the feedback, which is the estimated state of the object during the flight. So because it's half a second, slightly over half a second, you got only like about 70 to 90 frames to deal with. So there's a lot of work on the impact on restitution, from Newton's kinematic restitution to Poisson's kinetic restitution to Strong's energetic restitution. And there's also work, graphical work done by Dabu, and also Roos, and the modeling, frictional impact by Cater, and then, Mason and his former student Yu Wan, and then there's LCP modeling, and then there's sequencing of the impact, multiple impacts into, sequential events. And then more recently, there's some work on multiple impacts, simultaneous impacts by Strange and Professor Liu's group in Peking University, and myself, my former student. And also there's impulsive manipulations for sorting and ping pong playing and batting and tapping. So, and the modeling of the impact with the environment is also an important part, and that has been looked at as well, done by Professor Zen and Ohio University, and then there's Bo Pankosla and Ian Walker. So, and recently there has been some work on catching in-flight objects, and the most known work is Professor Billard, who's going to be a speaker later in a workshop today, of catching, very impressive catching objects by, moving the one upon the impact of the hand with the object and just basically move back, follow the trajectory to reduce the impact and for the catching. They didn't model the impact, but it's dynamic manipulation. And then there's the table tennis robots, the first tennis robot by Anderson. And the most impressive one was actually designed by a group of researchers in Zhejiang University, led by Professor Xiong, whose robots can actually rally over 170 strokes. All right. So now let's get to the technical side. So what is the impact? We're looking at it, 2D impact. One is the bat, the other is the object. Okay. So the equation can be, the central equation can be written very succinctly. And so you have the contact velocity, and then this is the inverse inertial matrix. Okay. And then that's the impulse. Once you get the impulse, you get everything basically, because the impulse, and you get the velocities of the object and the bat, and you get the contact velocity as well. So let's say if we get the impulse in the end, okay, but the impact happens within a split of a second, right? It's usually 1/10 of a second. And then you will be able to plug into, Newton's equation and Euler's equation to get the post-impact velocity and angular velocity of the object, which is, in our case, is subject to the constraint of taking the object to the target. So the central question is how to determine the total impulse. So we have, this is the relationship here. We have the impulse, which through the Newton's law decides the contact velocity, okay? And contact velocity via Coulomb's law will characterize the friction mode, which will affect the impact. And it also dictates when the compression phase ends. And in the meantime, though, at the contact, there's potential energy accumulating in the first phase. That's during the rest of compression, and then released afterwards, after the contact velocity becomes 0. So there's the relationship between the impulse and the energy, because we're using energetic restitution, so we have to be able to track that, okay? So what we did is basically, we project this impulse along the normal direction and in the tangent direction. The same way we'll project the contact velocity. So there's a case-by-case analysis. This is the work that similar work has been done, back about 20 years ago by Man Mason and Yu Wan, but they were using kinematic and restitution, kinetic restitution, Poisson's, and we're giving a more compact solution to this. So there are special values for the impulse. So impulse, the normal impulse is the only variable. All the other ones, the tangential impulse, the contact velocity, the energy, potential energy, all of these are functions of this variable. So there are several moments that are critical. One is the end of the compression, that we have a value of this normal impulse, and then the other one is when the tangential velocity becomes 0. And then there's the third one is the end of restitution, because we're using energetic restitution, so we kind of attract the energy, okay? And then you look at track the contact modes as well, and that is under the Coulomb friction. Okay, so there's 3 kinds of modes. One is a stick, and then the other one is slip, and then there's a reverse slip. Okay, so here it basically will give you an idea. And if you imagine this bat as a ellipsoidal object, and then the object is this pentagon, and then so by adjusting the coefficient of friction, contact friction, and also changing the other parameters slightly, we can generate all possible scenarios. These 5 are all the possible scenarios. The first scenario is that the contact slips throughout the impact, okay? And you see this is the impulse here, and on the right, this is the contact velocity. So they are all linear, straight line. So the other one is when the slip contact mode changes into stick contact mode. Okay, so this hollow dots here represent where the contact velocity becomes 0. If you focus on this black curve, okay, so that's where it goes to 0. After 0, it stays at 0. Okay, but that happens before the compression phase ends. Okay, so there's another situation that happens for the slip transition into stick, but it's during the restitution phase. So it's after compression ends. Okay, and then you can also prove that the other mode, if it after slip, the velocity becomes 0. So if it does not stick, then it has to slip, but the slip will have to happen in the reverse direction. So that's the reverse slip. Either happens during compression here, or in the end, last scenario during the restitution. Okay, so impact has been studied by a lot of researchers, and one thing seems to have been neglected in the past is, okay, so you're using Coulomb's law of friction, to model tangential impulse and contact, and then you're using either, kinetic, kinematic, or energetic restitution. Are these laws, fundamentally consistent with each other? Okay, which means that, is the impact of the termination of the impact guaranteed or not? Okay, so we like to ask these questions. Will the contact velocity always increase to zero? Because, at the very beginning of the impact, it's actually along the inward normal direction, right? So after it gets to zero, will the energy, the potential energy will decrease to zero to end the impact? That's another thing we have to worry about, okay? So for 2D impact, it is easy actually, using some proof, and you can show that, this normal contact velocity will eventually be increasing at a constant rate. And builds on that, we can show that the impact process will end. Okay, so Coulomb's friction and this energetic restitution law, they are consistent, right? All right, so that's what happens within that, a tenth of a second of the impact, right? But after the impact, the object takes off, okay? And it's supposed to go to the target. Okay, so that is the open loop. We have no control. So we like to understand the mechanics behind it, okay? So when the object is flying though, it's subject to two forces in this case. One is the drag force, which acts in opposite to instantaneous velocity, okay? So this is typically modeled empirically using this drag coefficient, and then, scaled by the cross, the area of the normal cross section, okay, which is normal to the velocity. And then it's quadratic in terms of the current instantaneous velocity. And then the other one is due to the friction between the air and the surface of the object, okay? And so the air is actually moving with the object, which actually creates different speed of the air and different sides of the object. So when you throw a ball, if it's backspin and it's gonna flow further, fly further, if you use a top spin and it's gonna land earlier than expected, or another example is from soccer. You can do the banana kick, make it bends outward or bends inward, depending on which part of your foot touches the ball. Okay, so that Magnus force is always orthogonal to the velocity, okay, and in the planar cases also orthogonal to the z direction, okay, which is the outward, okay, so direction. All right, so after you have these forces now, of course, you have the dynamic equation. So you get this Newton's law, and that's the differential equation. But this differential equation, if you numerically solve it, then you're kind of doomed, because for planning, you would have to, adjust the bag positions and the, the robotic arm positions multiple times, which means that you have to do planning many, many times. But this numerical solution is too slow. Okay, so the simulation cannot be done in real time of half a second. So what we actually did is we're looking for a closed form solution. So we basically replace this right-hand side, the velocities, with the closed form of velocities under gravity only. So we're ignoring, the air forces, aerodynamic forces. Just use a simple form on the right-hand side, but on the left-hand side, we let it be. So we actually are able to get a closed form solution to this ODE. And then we did some verification here, using three objects. One is a ping pong ball, the other one is a dumbbell, okay? And the third one is just the block. If you look at this first flight diagram here that has three trajectories, the real trajectory is this dashed black trajectory. It happens within a 0.6 of a second. If you don't model aerodynamic forces, and then the red trajectory is where the ping pong ball is going to, okay, which is going to be way off the real trajectory. That means if you're using this for your planner, okay, and then it's going to be misled. And if you use our approximation, and you get the screen trajectory, which stays very close to the real trajectory. We also did the experiment with the dumbbell object and then this block here. And then in all these cases, it turns out that the approximate solution is very, very close. The trajectory is very close to the real trajectory. Okay, so that seems good. And of course, and the object is flying towards the bat and then the robotic arm, you have to constantly do the state estimation in order to adjust the arm and set the right velocity, joint velocity at the time it meets the object, and to program the impact. So so we use this flight estimation. We do two kinds. We're kind of mixed EKF, extended common filter, with the least square fitting, and we find out. So one is used to estimate position and velocity. The other one is used to estimate orientation and angular velocity. So here's just a simple illustration here. This red horizontal line is the estimate if you just use EKF on the angular velocity. Okay, and so it really doesn't change. And if we use these squares, okay, fitting, we actually get pretty close, to the real trajectories, and as the object keeps flying further. Okay, and then so this one shows the fitting results over 45 frames and 86 frames. So the A is the real one. Okay, A is actually the modeled one, and then the real one is right here. It's taken by the image. It's the frame, that particular frame, and then that is very close. So in this case, the batting I think happened at around 90 frames. So when the estimate is good enough. So now we have to program the robotic arm. So what's the arm pose? As we know, though, if you pick the contact point for where the impact happens, basically the joint angles are uniquely determined. Okay, so the arm we're using is the 4 degrees of freedom RAM arm. So we're basically using the joint 2 and joint 4 because it has only these 2 degrees of freedom that in the same plane. Okay, these are used for batting. All right. And in the meantime, this RAM arm has constraints over the joint angles, velocities, and accelerations. Okay, so we get the angles and we check whether they're in the range, right? Okay, but that contact point is not predetermined. So, for instance, if you fix the moment of the flight during the flight of the object, and then the contact point on this dome-shaped object is going to be, around the circle here, right? So you have a one-dimensional set of contact point, which is going to give you a one-dimensional set of poses. Okay? So that is good because we don't want a unique pose. All right, so now impact planning now, we describe the state of the arm at the time of batting using 4 variables, the 2 joint angles and 2 joint velocities. And then there are a host of constraints, there are a total of 16 of them. Only 2 of them are equality constraints. One is a path constraints. After the impact, the object is going to fly to the target. The other one is a contact constraints. These 2 equality constraints reduces the state variables to 2, okay? And then all the other ones are kind of like inequality constraints we can deal with. These are very, by checking whether it's within the interval or maybe convert the condition into a first order logic formula and then use root finding to check the truth of it. All right, so planning now comes, okay, we divide that flighting time of slightly over ½ second into cycles. Okay? So every frame represents a cycle. So a cycle starts when a new image frame is taken. At this moment, though, the robot arm is still following the old trajectory. Okay? But now with the new image taken and image processing and the feature extraction and do the state estimation and then the planning. Okay? Now, at the time of impact, the velocity, joint velocity and joint angles the robot is supposed to achieve now has changed. So now there's a new trajectory. And so here, that is about 3 milliseconds, and then the new trajectory takes effect, okay? And it'll last into the next cycle, okay? Even after the next image is taken. So the robot basically constantly modify its trajectory. So here we'll just give you an idea how this happens, at the very initial frames, and so these estimates, so these estimates V1 and omega 2 represents at the moment of batting, supposed batting moment, and then joint angle and joint 1 and angular velocity of the second joint. Okay, so and later on, and they are more and more concentrated, so that which means that it seems like they have reached a consensus. So the camera we use, this is hardware, it's a Ximea high-speed camera that can take up to 1,000 frames, even though you get only very small image frames that way if you wanted to do it, because our flight is in the plane, okay? And so we are able to use this image grade and, just to calibrate it and get very, very accurate result. Okay, so we want this object to fly in a vertical plane. That's why we use a launcher, catapult. And these three objects, we did measure their drag coefficients and Magnus coefficients and coefficient restitution and contact friction. All these are measured. So now let's look at some video. So we did 4 sets of experiments. So here's a hanging board, okay? And then every time we just do one batting, if it hits the board, it's regarded as a success. The next one is just basically bat this dumbbell object to, to knock down these toy bowling pins that are in a row situation. And you see here's the miss, actually. The success rate for this is not really that high. This is a very, very skillful task. So what happens here, this video is made by Matthew that shows you, the object starts flying, towards the robotic arm, and the planning is going on, and you see the trajectory adjustment, the anticipated trajectory pre and post impact trajectories are adjusted until in the last few milliseconds, and then it does not very much, and then it's supposed to go to the target. Okay, so in a third one is to bat this block into the net. And Xiao Qian is actually throwing, so he has practiced a lot just to make sure that it's thrown within the vertical plane. But of course, there are some errors. So it's nice to see that some of these successes despite the errors. Okay? This is all taking in one shot and just bat into the nets. Okay, and then it starts having misses. But this is actually easy because the aerodynamics modeling is more accurate for spherical objects. Okay. So this is another one. I think this is the last one. This is the 5th one. And so bat the ping pong ball to hit it towards, the center point of these concentric circles. As the closer it hits the location is to the concentric circle, the better the accuracy, right? Now it's using a different pose for the robot to do the batting, okay? And this one is actually very close, okay? So now, this is the superposed snapshots will show you basically what happened, help visualize, the second batting task of knocking down bowling pins. All right, so we did some measurements here, and these green dots represent the successes, and these hollow dots represents the failures, basically when it hits the board, and it's a success, okay? When it's off the board and it's a failure. So this is very good because we're batting a ping pong ball and then the aerodynamics is good enough, 50% of success. For the bowling ball, and you see that success rate is actually not that high, it's pretty low. We did 182 throws and then there are only 50% success. For this particular set though, there are 20 of them, we have 5 success, so this is the one of the higher, one of the groups with higher success rate, okay? And we actually also did some comparison with Xiao Qian standing here trying to bat that herself without training. Okay? So her successes are marked here. And you see that this is the difference between a robot and human. Actually, as Xiao Qian is batting more and more, she was getting better. So her success rate was actually improving, and then so the, but despite that, because she had received no training at all before the task, and in this set, her success rate is slightly lower than the robot. Okay, and for this one, I'm just skim through this. It's about 20%. This is also a tough one because just like the dumbbell, and then the a lot of the failures for the dumbbell is because the dumbbell the flight of the dumbbell does not stay planar. It just fly off the plane, and then the robot will have no way of getting, sometimes even knocking the dumbbell. So in this case, it's still, even though we're using a launcher, it's better, the situation is better, but because, this is not a spherical object, and we had a success rate of 20%. So here we did a comparison between the last group. We did a comparison between the robot and Xiaoqian. So the robot was able to succeed, 25 out of 37 instances, and Xiaoqian was able to succeed, half that rate. And you also see the difference between robot batting. This red crosses basically has no bias towards the, in terms of directions, whether left-hand side or right-hand side. Whereas Xiaoqian seemed to be a little bit right-handed because all of her hitting positions are kind of slightly to the right of the center of the circle. Okay. So that's the batting thing. After that, we wanted to move on to 3D batting, and then Matthew noticed that, okay, but first of all, how are we going to deal with this motion estimation of the flying objects? We realized that this can be a problem for itself. So Matthew spent the last 3 years of his PhD working on this problem. So he was never able to come back to 3D batting. And so this has a lot of applications. There's a spacecraft, altitude estimation and tracking debris and asteroids. And, for catching and batting, you have, like we just show, and also for human training in sports, and virtual reality and underwater explorations are potential applications as well. So here's a diagram for this task. Basically, we have, the observables are the features of the object during the flight. And then we have to set up this dynamic system using aerodynamics. Now it's 3D, and then using a common filtering, okay? And then we do the pose and motion estimates. But these features, we use 2 cameras. These features, they only appear in a number of frames and they disappear. So we have to track these features. We use a planar graph to do the feature tracking, and have, every hypothesis will set up a correspondence between the feature and then the image points. Okay, so there's a lot of related work from, velocity estimation, vision-based, and kinematics-based using accelerometers, magnetometers, and also the aerodynamics, pure aerodynamics. As that's the route we're actually going to follow in terms of modeling dynamics, and common filtering from the initial work by Common, and then there's also the extended Gaussian common filter, Smith, and then there's the unscented common filter, and all these and done by people from filtering and control, and also from vision, and then there's also the VINS recently. Mostly for mobile robots, and the constrained common filtering, and more recently the IEKF, the invariant EKF, which basically tracks a state in the using the algebra. Okay, so the NE groups, basically the transformation groups, which automatically satisfy the constraints, such as unit quaternion to represent orientations. Okay, so then there's some work from computer science side for the planar graph matching. So what happens here is that, during the flight, the object has a velocity and angular velocity all in the body frame. So it's subject to the drag forces, which is typically modeled using using an empirically. And then there's also subject to the Magnus effect. Okay, that we have empirical formula for that. But in the meantime, though, because of the velocity, it generates velocity potentials. You would have to solve the Laplace equation to get that. And then from the gradient of that, you get an air velocity. Okay, and so they plug into the Bernoulli's equation to generate the air pressure, and you integrate over the surface to get, the lift forces and then also the torque. Okay, and you combine lift force with the drag force, you get, force and torque, on the object, and then you apply, that to the Newton's and Euler's equation, so that to close the loop. All right. So what are the observables? So we have 2 cameras right here, FC and FC prime. So you have these feature points here, for instance, like a vertex of this polyhedron object. And then it's in the body frame, converted to the world frame, and then the camera frame, and then perspective projection, and then the torsion, distorted the image, and finally get the image point. Okay. So that will conclude the loop. So the system observables are, the images of the point features, and also we use the, because of these two cameras in the epipolar position configuration, so we use the normal epipolar planes for these features. We get, 27 variables, including, center of mass and object orientation by quaternion. We also have the camera orientations because the camera orientation is not exactly known, even though they are known to a good approximity. And then we have the velocity, angular velocity. We also have the camera's focal points. So, okay, and then you combine these camera dynamics and the object flight dynamics with camera projection, okay, and then so you get this dynamic system, and you have the observables. So now it's subject to 3 quadratic constraints on the quaternions, because these quaternions have to be unit quaternions. So what we're doing here is to use common filter to minimize the posterior covariance, and we exert these constraints using Lagrange modifiers, make sure that the state, stay in the SC3, basically, okay? So this is kind of like equivalent to the IECAF, invariant ECAF. We get the common gain, all right? So now, one big hurdle here, obstacle, is to track the features, okay? So let's say we have the model of the object, which is this polyhedral, which can be represented by this planar graph that captures topological structure of the object. Okay, every time though, the image is only viewing a partial object. So we set up from this feature extraction, we set up an image graph, and then we have to hypothesize the correspondences between these vertices in the image graph and those vertices on the planar graph, which are essentially the vertices on the polyhedron. Okay? So we basically maintain multiple hypotheses. For every hypothesis, we just give it a common filter, and then we kind of evaluate these common filters, let them compete, and then delete those that are inadequate, and also generate new ones. So by doing this, we're able to do the tracking. So we did some verification here, and one of them is to use the wooden frame and using accelerometers as independent validation. And the second one is to use the rugby ball and flowing, and this is aerodynamics. We use the quadratic constraint common filters with aerodynamics modeled, okay? And then as you wonder whether aerodynamics really helps, okay, we did measure using the reprojection error to compare 2 versions of common filters with or without aerodynamics. As you see, the errors with aerodynamics is consistently, here represented by this black curve, okay, consistently below that used without modeling aerodynamics. Okay, that's for the first camera and the second one as well. So now here's where we use this feature tracking for this polyhedral objects. And then on the right-hand side, these are the snapshots taken simultaneously by the cameras. And you see that here on the bottom right, you have this hypothesis generated, lasted for a while until both are killed. Because every time, when one vertex, some occlusion happens, vertex disappear or appear, and then the algorithm would have some difficulty tracking the features. And sometimes you would have to regenerate hypotheses, which is not really a problem because this new generated hypothesis number 3 here and the lower end, bottom right, is able to track this very well. Okay, so as I'm running a little bit off, I'm running close to time. Okay, I'd like to just mention some of the future work, which is supposed to be future work for Matthew, but he has graduated. He's now happy with Boston Dynamics, so it's all behind his mind. So we like to do this 3D impact modeling more efficiently. I had some work with my former student, Fei, who's working at Disney right now. And on 3D impact, we're able to compute these things and do the validations, okay? But efficiency is is a headache. And if it's not efficient, you cannot do the planning, because as you see, there's multiple plannings have to be carried out. For every frame, there's multiple plannings, and you got, 70 frames. Another thing is about the Super Bowl, phenomenon of modeling tangential compliance. So the tangential impulse is not all dissipation. Some of it actually can store part of the potential energy generated during the impact. And also the trajectories, it would be nice to actually have general trajectories, non-vertical trajectories, just like the banana pick trajectories, for the soccer ball. And we like to do all this in real-time estimation. This is going to be very challenging because, as you see, time is very short. It's only slightly over half a second. I'd like to end this with an acknowledgement. And I think I still have some time in case people are interested in asking questions.
Thank you, Yanbin, for your great presentation. I learned more details of your impressive frictional impact dynamics model now. Are there any questions? If not, maybe may I ask a question, Yanbin?
Sure.
Yes. So basically, in the paper, I think we covered the case that when the inertia between the robot and object is drastically different, whereas in practice, that this assumption might not be always true. For instance, in these box grabbing examples or more common impact tasks, the inertia, the object inertia is kind of not negligible compared to the robots. So in that case, how can we, what kind of robot inertia should we use? How do we compute it?
Yeah, that's a very good question. It's actually, it's a deep question. So here, you're getting into the technical details here. We're kind of regarding the object, mass is negligible. It has mass, but it's negligible relative to the robot mass, which is regarded as infinite. And I think there have been some work like by Khatib's group on this, modeling this robotic arm, the inertias during impact. I think, but they are using Newton's kinematic restitution law for the modeling. So maybe we could plug in that, or maybe use that, and then try to see how to fit in this energetic restitution model.
Okay, thank you very much for the answer. If there are no more questions due to the time constraints, we need to switch to the next speaker. So Yanbin, thank you again for your presentation. And our
My pleasure.
Yes, and the next presenter is Dragomir Danchiv, or his preferable Japanese name, Yoshikatsu Kanamiya, from Kaishi Professional University. And the title is Emergent Humanoid Robot Motion Synergies Derived from the Momentum Equilibrium Principle and the Distribution of Momentum.
Okay, so hello everybody, and thank you very much for your interest in my talk. I would like to thank also to the organizers for giving me this possibility to introduce my work here. So my title is quite a long title. I will pick up some keywords from this title during my talk. So the main aim is whole body motion generation, and especially I'm interested in quite dynamic motions, how to generate dynamic motions. And the secondary aim is how to realize these dynamic motions using a controller. So I hope you will be interested in our control structure that is not only for dynamic motions, also for tasks like multi-contact control and so on in real time. So our point is to generate all these motions and these tasks in real time. So this is the outline of my talk. First, I'll give a brief self-introduction, and during this self-introduction, I'll try to explain the idea, where we got this idea about the distribution of momentum. Then I will go on with a hypothesis that is used in motor control of human motions, and that humans use synergies, muscle synergies, kinematic synergies, to generate the motion, various motions. Because I want to make use of this hypothesis. Then I will give you some overview of emergent motion generation in robotics, because this is not a new problem in robotics, but maybe some of you know it, maybe some of you are not so familiar, but it's important to think of this and why is emergent motion generation is so important. After this, I will introduce the momentum equilibrium principle, which actually is well known in balance control with respect in humanoid balance control with respect to the linear motion, but it has not been considered with respect or in-depth considered in respect to angular motion. Okay, I will move on then with to explain our multitask control design approach, and finally give you, I have prepared a number of results, mainly simulations from simulations for balance control while standing or while walking, as well as a number of acrobatic performances generated with our controller. So from my studies, actually, when you see here the dates, it's 40 years ago, a long time ago, I started with my PhD study. So during this 40 years, I have picked up here for this talk 5 topics. One is kinematic redundancy, one is parallel link manipulators, another one is about the free-floating space robotics. Then I will talk something about singularities, so the so-called singularity consistent path tracking, because this is also important in whole body motion generation. And finally, about the main topic of today's talk, about motion generation control for humanoid robots. So at the start of my PhD, in our lab, we had actually 1980s. It was the time when industrial robots were hot topic. So in my lab, there was an industrial robot, and we had 6 degrees of freedom arm. But luckily, or it was at that time, it was not so lucky for me, but it was mounted in a slider that was also servo controlled. So I had a manipulator of 7 servo controlled axes, and I have to. My task was to solve the inverse kinematics. Now it's very easy. But we came up with, I came up with this equation here, and as you can see, it's quite familiar now, but at that time it was the first paper where it was published. So you have nested null spaces. One is the Jacobian null space, and another one is the remaining degrees of freedom null space. So later this method became known as the task of priority method. So after my PhD studies, we started working on a topic about actually parallel topology manipulator. My colleague, Dr. Sotiro, found out something about these parallel manipulators. They were not very well familiar in the robotics community at that time. And we designed a controller for force control and made a simulation for this packing hole assembly, which was also a hot topics for industrial robots, packing hole assembly. So further on, a bit faster forward, in the 80s, I moved to Japan, and there was an idea to walk to free-floating space robots were quite a hot topic at that time, and it's Professor Metani's laboratory. So I came up with the idea to put on a redundant, kinematically redundant arm on a satellite base and to see what happens. So this was the first time that I came across this equation. This is the angular momentum equation, which has a 0 on the right side, because in zero gravity you have the conservation of angular momentum. So this equation has 2 components, one for angular momentum for the satellite base and one for the manipulator. And the coefficient matrix is the coupling inertia matrix of joint velocity, actually. And I was looking for a similar solution like in redundant robots. So find out that the null space of this coupling inertia matrix can be used, like in this equation on the right side. This null space later we call the reaction null space. So I will explain how we can use this reaction now space. And this work, 1992 actually, this gives you two different examples of a free-floating robot. One on the left side is when the end-effector trajectory is constrained within this reaction null space, the null space of the coupling inertia matrix. In that case, there is no attitude deviation of the satellite base, which is quite important. In the conventional way, if you don't have this, if you don't use this reaction null space, you have a deviation in this satellite base. And the deviation of the satellite base is very unpleasant because you have a communication link, you have an antenna, and if the antenna changes orientation, you lose this link to the Earth base control station. So it's very unpleasant. Actually, we were lucky later on, 10 years later on, there was a experiment in space of a real space robot with the Japanese space agency. And we were lucky to try this reaction null space-based approach. And it went quite successful. So with this project, it was called ETS-7 mission, actually. There was a satellite base and a manipulator, and there was a smaller satellite that was attached. And then it was supposed to be detached and then retrieved with the manipulator arm. So there was a docking problem. The manipulator arm had to dock with this sub-satellite to retrieve it. This was, of course, a very nicely designed because the approach and the docking was very, very slow so that you don't have impact. But similar scenarios when you have to deal with space debris, so a lot of flying objects are over there, you don't want to get involved. So if you want to try to get this debris with the manipulator arm, like this, you have an impact. So when you have an impact, what you've got is, during the impact, there is no control. So you've got just a jump in the joint velocities and a jump in the satellite base angular velocity. And as is usually the case, you have here high gear ratios in space. It's not so nice like Patrick reported. We don't have this type of nice gear ratio set. But if you have this, that means the joints are nearly locked. Then you have the behavior of the system like a composite rigid body. If you have a composite rigid body, that means delta theta dot is minimized, almost zero, and delta omega b is maximum. So you have a lot of change of attitude in the satellite. As I mentioned, this is not desirable. What we came up with this idea is to work on post-impact control instead, because we cannot do anything during the impact, which is very short phenomenon. So for post-impact, we proposed base angular momentum damping. We rewrote this angular momentum conservation on the left. We rewrote it in terms of joint accelerations in order to deal with have a higher bandwidth response. And we used, like here, feedback gain for joint damping, joint velocity damping. So in this way, it is possible to swiftly transfer the momentum to the arm. Why is this needed? Because if you swiftly transfer the momentum to the arm, the base is not so disturbed like in this. But anyway, so you transfer the momentum to the arm, so the arm starts moving very fast, which is eventually the joint will hit the limits, which is also not a problem. So what we have to do, we have to get rid of this energy. This is a little bit, I'm explaining about this because a little bit different than in Earth-based robotics, which everybody is doing now in humanoids, but we can learn, I have learned from this, about this momentum distribution. What is this? This momentum transfer. So the manipulator arm is moving fast. So what we have to do, we have to bring back the momentum to transfer it again to the base. Why? But we do it slowly because it's a matter of time. So we do it slowly. In this way, we can use the reaction wheels. There are reaction wheels in the base and store the energy, impact energy in the reaction wheel. So it's a momentum transfer and energy transfer. If you store this in the reaction wheels, later you can use then the jet thrusters to get rid of this eventually. So this is one example. I hope I could explain to you why this momentum transfer is so important. And it is similar. We have similar studies in human body control about such momentum transfer. Imagine tennis serve. There is a study about tennis serve. So if you serve, you have to generate angular momentum and you have the player has to transfer it to the racket so that it has to hit the ball in an optimal way. So this is also such an example of momentum transfer I'm going to talk about today. Okay, so another topic about motion generation, which I found very important in humanoid robotics as well, is the problem of kinematic singularities. So 1995, there was this publication, I made this publication, and the method to deal with so-called ordinary singularities. I'll explain in short what that means. So the method is, I think you will understand first in this equation number 3, you have, this is the forward kinematics function, and you have an end effector path that is parameterized by parameter alpha. So I wrote this equation in this type of with end effector parameterization, and you see that this is not directly dependent on time, so it is autonomous dynamical system in the form. And if you have take the first derivatives, like here in equation 5, you get a vector field equation. And based on this vector field equation, on the right side I have a 0. Here I can put an error. So this becomes like here on the right side. So the difference between forward kinematics and the trajectory, the parameterized trajectory, desired anti trajectory. And this is a vector field zero dynamics control, which turns out to be quite successful in dealing with this type of ordinary singularities. In order to understand this, maybe you can think of a very simple example of a 2-arm manipulator, and the end link is required to move along a straight line. And on this left and right, it hits this workspace boundary, and this is singular configuration. And you can think of this system as a closed chain slider crank mechanism of 1 degree of freedom, like this. So we don't, when you think of this, we don't have any singularity. This singularity simply disappear from the equation. So the manipulator can come here and then it goes back by reconfiguring itself. We have implemented this with the real parallel link robot in 1994. It's a hexatype, all rotational joints parallel link robot. So the end link, the traveling plate, is following a straight line, and in the same time, the legs of the robot are reconfiguring. So like elbow, I said legs, but maybe hands. So it's elbow left, elbow right, and they change in this way. So the kinematic singularities simply disappear. This is used, they used to call it assembly mode in parallel robotics, because in order to change that configuration, it was thought that you have to disassemble the mechanism and to assemble it in the, let's say, from the right elbow to left elbow configuration assembly mode. So now with this control method, you don't have to think about assembly mode. So how is this related to humanoid robots? We have implemented this method for humanoid robots. On the right side, right down, you see some creepy motions we have in this way. So the legs are following, sliding on the floor, and in the same time, they are reconfiguring. And also the arms, you can do this with the arms. So some sort of creepy motions. So of course, some people don't like these creepy motions, and maybe they are useful. I hear there is a superhuman or a superhumanoid session, maybe in the humanoids, this year's humanoids. So maybe you can use it as an example of a superhuman or superhumanoids. But Since we have the uncanny valley problem, you can go on the left side. You can stop the motion, of course, of the singularity itself. And we have implemented also this for straight leg walking in 2006. This is just a static walk, and it is very clumsy. We have it now also in dynamic walk. So I finished this, and just to summarize or sum up, so my studies on humanoid robotics actually have three pillars, like kinematic redundancy for motion optimization, my studies on parallel link manipulators for force optimization, and the free-floating robot studies for angular momentum control. So kinematic redundancy I can use for multi-body control, parallel link manipulators for multi-contact control, and the angular momentum for enhanced balance control. Now, about the studies on motion generation, whole body motion generation. Actually, I was thinking all the time during these 40 years and so about kinematic redundancy, and there, of course, many methods have been introduced, pseudo-inverse, the most straightforward one, or some weighted pseudo-inverse, or some null spaces, and so on. But since we have to deal with the humanoid robot, it has a human-like body. So how to make this whole body motion generation? And what is the? And I came to this conclusion that we should expect human-like movements. And since we expect human-like movements, the people expect human-like movements, the conventional redundancy resolution doesn't work. We have to look into the way humans generate their motions. So motion capture is not an elegant solution, of course. So let me go on in this outline with the human motion generation hypothesis. And it goes way back to Hugh Links-Jackson, an English neurologist. Way back in 1889, he published this article, which he has very famous. He's saying that the central nervous system knows nothing about muscles. It only knows movements. So what does it mean? It means muscles. I think it good fits also with Patrick's presentation that you have a sort of passive dynamics. So muscles play the role mainly. You can name them for passive dynamics. But the central nervous system, it generates commands that relate only to movements. So this is a clear call for a task-based approach. Depending on the task, the central nervous system, there is a hypothesis, it generates some movements. And it does not generate the movements for each degree of freedom. What this guy, this is Nikolai Bernstein. It's in the beginning of the Soviet era. He was tasked with to study the motion of the humans, especially for labor. They wanted to become very skillful laborers. So on the left side, you see that his task, one task he considered this was hammering and chisel. And this was a very simple task because the arm moves fairly in one plane and the hammer is in one plane. So he could easily analyze it with these cyclograms. He used something like a motion capture, you say in the middle of this movie, I found. And so he could analyze, and he found out that there is a problem because the hammer, when the guy who was hammering, the laborer, he was trained very well such that the hammer always hits on the same place and always uses the same trajectory. But on the other hand, the arm, the motion in the segments of the arm was different from cycle to cycle. So he called this the degree of freedom problem. It is known now as the Bernstein's degree of freedom problem. So he was wondering, how does the central nervous system deal with this degree of freedom problem? By elimination of unnecessary degrees of freedom, it was rejected. This is not. By optimization. Our brain does not have time to optimization. So he came up with this hypothesis, and that there are synergies, or we call it the motor field. And he proposed a formulation in terms of coordination, motion coordination of these synergies. So he came also with this maxima that the most important function of the brain is the organization of movement. This is amazing, I think so. In the field of humanoid robotics, it's so important to think of this, that it's most important think of the brain, and we have to understand how this works. So there are simple synergies already known and used in humanoid robotics. Like on the left side, you have this, in the sagittal plane, the ankle strategy, when you have a slight push in the back, and then you stronger push, you have this hip strategy, and the stronger push, you have the step strategy. And on the right side, there is a similar, or in the lateral plane, you have, again, depending on the push, you have different synergies. And factually, the synergy analysis in the field of biomechanics and physical therapy are used a lot of, and these are some recent studies. So especially Professor Latash is very known in these studies. One thing which I want to relate to our control design is the Bernstein's description of synergy. He said that the coordination on net of the motor field is non-rectilinear. So we have some nonlinear stuff, and it oscillates like a cobweb in the wind. So this oscillation, however, does not destroy the topological relationship. So topological, there is some topology in this. So he said either of zero order or the first, perhaps even higher orders, he thinks. So this sounds like an almost autonomous dynamical system. You have a topology there. And then the task synergies you can view as motions on a slightly time-varying manifold in motor or in joint space. And the variations are used to compensate internal and external errors. So like this hammering task, the hypothesis is that each time the hammer is trajectory is the same, but the arm compensates for some errors, like small internal errors or possibly some small disturbances and so on. So this topic, actually this is confirmed. We have a manifold, it's called the uncontrolled manifold or the UCM concept. And this is hot topic because we have a very recent paper, the uncontrolled manifold. So the manifold is determined via its tangent bundle in differential geometry. And that is with the help of the null space of the task Jacobian. And because it is null space, there is an idempotency property which preserves the topological structure. So this fits very nicely in the hypothesis. So I will come back to this later in design and our control design. Now let me go to a brief overview because the time is quite advancing. Overview of emergent motion generation that are used in robotics. The synergies have been addressed in robotics. In the 1970s, especially Vukobratovich studies, mainly in relation to a human robot. So walking gait synthesis, actually. They use walking gait synthesis. They talk about synergetic rays, that we have to use some types of synergy in this, but it was not very clearly formalized. Also in the 70s, later in my studies in redundancy, I used a lot, I refer to this paper of Alain Lijoie in France, and he was talking about synergy when resolving the redundancy of a 7 degrees of freedom arm. Much later, so in the 70s, there was some talk about synergies, but then there was nothing. And after the millennium change, we have now some synergies started appearing. For example, these are some in the area of grasping. So because grasping, you have also so many degrees of freedom in the fingers, you have to, they found out that we have to use some type of synergies to get, and this later, this third paper has some formal definition of a grasping synergy. And we have also, as I mentioned, the synergy and balance. The ankle and hip strategy first appeared 2002 in this paper. Later in Goswami and Kalem 2004. We had implemented this with HOPE-2 robot using the reaction null space. We use the reaction null space for the hip synergy. And a nice, very nice paper is this one, which has also a formal definition of a synergy. I will give you an example of this use of the reaction null space we made 2016, some 5 years ago. We made this type of experiment. So we asked, we put this guy on a slider without any damping. And we asked him to make just a squat, and trying not to move the slider as much as possible. But as you can see, this was not possible because there was an imperfect movement. Maybe we did not go so far, but if you try very hard and you learn this synergy, maybe you'll get very perfect and almost keep the slider without any movement. But I think this is very difficult because there is some time delay in our central nervous system. It's not about 200 milliseconds. It's very important, this time delay, for dealing with this imperfect. So when I apply the reaction null space on the right side, you see we can get reaction, less movement, perfect reaction and movements. And that is what I want to aim in motion generation, to design perfect dynamic motions as much as possible for a given task, because this is a task-dependent issue. So I want to talk about emergent movement synergies and explain with a simple example, again with this 2-arm manipulator example, to show you that what is about this simple synergies, that we want to generate a complex motion with a simple command. This is the main point. And we found out that if you have this type of 2-arm manipulator with equal link lengths and they are overlapping, then you have a bifurcation singularity, because you don't know if you apply a command that pulls down or along a reference path that pulls down in the same, it's aligned with the links. So there is no way that this system knows, the robot knows how to move. It stays like this. But if you have a small deviation from the perfect, let's say 180 degrees in the second joint, if you have a very small, infinitely small deviation, then we know that the system will start moving either right or left. In my case, it's right. So it results, if you apply this command, it results first in a pure rotation of the links. So the end link does not move, almost no more. You cannot see with the VAR that it moves. But it, because 90 degrees rotation, when it becomes orthogonal to the command, then the end link, the end effector, the end tip starts tracking the reference path. And you have stage 2 tracking the reference. So this is an example with the same command, and it generates a quite a complex motion. I will show you. We applied this to a humanoid robot. So you can see on the left side what I have. I have a commanded COM motion velocity upward. Just a simple command for the COM motion upward. And on the left side, I did not constrain the motion of the arms. So you can see when the legs are extended, they go to singularity, and the arms continue moving, because with this motion, the center COM command is still valid. So it can move up with this motion. On the right side, you can see that I constrain the hands not to move, but because the redundancy of the arms, you have 1 degree redundancy each arm. So they they change the configuration from elbow down to elbow up with the same command. So this is an example how you can generate this type of motions. Okay, so So there are some emergent movement synergies used. These are well, I hope you know them very well. In humanoid robotics, like Goswami and Hare, you have this about spin angular momentum relation. In Delasa, in animation, and some recently worked also. We have as arm swinging, as also the work of Patrick in 2013. You have upper body emergent motion, jumping and kicking, and so on. And recent work which Patrick reported now about the Cheetah tree robot. I think this is a work related to this one. Okay, so let me go on with momentum equilibrium principle. Now, I think that everybody would agree that angular momentum plays an important role in enhanced balance control, and it has been linked now I went very fast through this overview of the emergent motion generation, but the arm swinging, there was a toe off, emergent toe off, and also hip shoulder counter rotation. These are examples of such emergent generation. So the open problem is, however, how to distribute this desired angular momentum among the body segments. So you have desired angular, but how to distribute it? Yeah. So there you can get some emergent, like arm swinging. It's fairly simple. You can get it, and toe off also, not so difficult. But how to distribute in more complex motions? So I start on with, again, with the angular momentum equation. On the right side, you have the angular momentum. I have rewritten this in terms of centroidal angular momentum. And therefore, here in front of the base or base link, we have the CERBI and the composite rigid body inertia tensor. This is the coupling inertia, the same. So you have something which I will call system angular momentum, it's a centroidal angular momentum. So I have a CRB angular momentum component, and I have a coupling angular momentum component. Now I can solve for the joint velocities using, for example, the pseudo-inverse of H omega, and get when I know the LC reference and omega B reference. So I will use this type of model to apply this. So this is a robot model. It has a torso joint with 3 degrees of freedom. This is important to generate very human-like motions. So using this pseudo-inverse, is it the best way to distribute? Now, let me go a little bit farther. I can simplify and rewrite this angular momentum equation in terms of angular velocity. So I use it like this by defining j omega. So I use the inverse of the CRB tensor. It's always positive definite. And I define the omega c system angular velocity. Okay, so it's actually, these are equal equations, but it's a little bit easier to understand. So I have CRB angular velocity component, coupling angular velocity component are the 2 components. Now let me talk about the momentum equilibrium. So we use this idea for inverted pendulum, and balance control is very known, ZMP manipulation-based balance control. And this is a relative motion phenomenon. What about this in the angular momentum? So we can rewrite the angular momentum, angular velocity equation in this way, put the coupling velocity, angular velocity on the left side. On the right side, you have a finite difference. So you have a CRB motion, we call this the relative angular velocity, actually. So you have pure motion and a CRB motion component. And this is the dynamic equilibrium for angular momentum. Coupling angular momentum, angular velocity is always in equilibrium with the relative angular velocity. So we use this in controller design. And we can use it for balance stabilization task, feedback, or we can use it for 0 relative angular velocity by using a motion in the reaction null space, balancing on a pole task. There is no feedback at all. So let me show you this. So if you see here, this is a feedback. We use a feedback here for using a feedback from the sensor for the angular deviation of the foot. You get an impact, a very strong impact. So the robot is first in conventional control, conventional balance control. And after the impact, so if conventional balance control continues, you can see here the omega F is the indicator for destabilization. So it goes very straight up exponentially. It will be destabilized if you don't use nice control. So we have here relative angular velocity, zero dynamic stabilization in this case, and it can swiftly destabilize, and then the motion will be recovered. So this is an example of graph stabilization and recovery. And on the other hand, we can put the robot on a rotation on a pole. It's a point contact actually. This is an unstable posture initial. And we can use just a feed forward RNA stabilization to stabilize. So the arms are free to move, and even it can forward bend. You can give a forward bend desired, it destabilizes, and immediately after this it stabilizes again. So it's so like a super stability for this. Okay, so let me go on with our motion control design. So what we do is we use this omega B and omega C, this relative angular velocity based angular momentum design, and we also use conventional COM design component and end-link component, which includes the Jacobian and also includes the contact maps. And on the right side, this is the desired spatial velocity of all the end links. So in order to make a nice design, we have to make some, we have to remove, for example, the motion in the hands. We have to make it through motion, so use these selective matrices. These have, you can select either selection in the COM motion or the base motion or the angular momentum motion or the joint motions of the feet, the torso, or the arms. So depending on the task, appropriate task components are removed. As much as possible, I want to remove. So the solution in terms of angular acceleration is like this. And I use simple control laws like this, feed forward plus PD, damping. For walking, we use DCM-based damping, and so on. This is also for this. We use also for this here RNS-based control and admissible angular centroidal angular momentum control. We use a weighted generalized inverse and the null space component we have here. So the null space component is just for postural control, as usual. This is nothing new. The weighting matrix is something more involved, but also not so much new. So we use two components for the weights. One is inertia-based, and one is range of motion-based, joint limit-based. So we can combine them, superimpose them by using appropriate setting with CRB inertia components for the base and with components from the complex inertia components. And we use here a threshold, which is determined like this, with this constant is empirically determined. So we have this type of motion. And you can see that if you compare pseudo-inverse based angular momentum distribution with weight-based angular momentum distribution, the arm motion is much more than this. So you can see also this is with some graphs in this. I will go very fast over it. It seems my PowerPoint is, sorry, this is the time is going on. I'm sorry. I have to, my PowerPoint was. Okay, so this is our control which we designed. It has these components for the control laws, hand wrenches, and so on. Okay, so because it's time, I will go very fast over this and go show you some results. So we have disturbance accommodation in single stance. This is reaction in single stance. This is when you have on the shoulder. This is when you have in the lateral plane. These are controls which we designed for walking, like arm swinging and combination with pelvis and arm swinging, also with toe rotation. This is how you can superimpose synergies, walking with sounds, arm swinging, a very large impact. This is a blind stepping on impact, and this is standing back flips. I'm sorry. So this is a standing back flips idea. I have no time now to show it. It's going some saturation of this. Let me see if I can again try it. Out of time, I guess. So this is a backflip which we generated. Okay, I'll go over this data. This is different types of gain. So these are variations in the parameters. This is a standing long jump simulation. And we have a professional-like simulation where the feet go to the ground, and amateur-like when you have with the feet are touching, and then you have toe rotation. In the end, we can simulate also like this. We have acrobatic others like standing front tuck and vertical jump. And currently working on this type of simulation. So this is my conclusion. I'm running out of time. So thank you so much for your patience.
Many thanks for your nice presentation. It's really great to know that some of the well-known equations are perhaps even older than me. Thank you very much. Are there any questions? Okay, so if not, maybe we can thank you, Nanchip, again for your nice presentation. I'm really impressed by the backflip. I think that is, if we can put it on the real robots, that would be very, very impressive. And but the simulation already paved a solid stone to this direction.
Thank you.
Thank you very much. So the next presentation will be given by Mehdi from AIST Tsukuba, Japan. And Mehdi is going to talk about the 3 laws of robotics subjected to unexpected external forces: estimation, rejection, and performance.
Can you hear me?
Oh, yes, I can hear you very well.
So actually, I feel a little bit sick, so I'm not sure I can do a long presentation. I will try to present everything, but maybe it will be shorter than planned.
Okay.
It's not coronavirus. We did the test yesterday, but still I have a sore throat. So
yeah, take care. I can hear your voice. Maybe take some more.
Yeah, sorry for that. Yes, so I'm sharing here.
Yeah, now I can see your screen.
Yes. Can you see the slides?
Yes, I can see the slides now.
Yeah, okay. Yeah, so it's a little bit provocative title because yeah, it refers to the 3 laws of robotics that are really famous for the science fiction. So the laws is to protect humans, to obey humans subject to the previous law, and to protect itself subject to the 2 previous laws. These laws are rubbish. Actually, even Asimov, who made these laws, the point of these laws is of his work is to show that these kind of rules cannot work. So it's more like philosophical thing. But I like the idea of having the laws. So I want to make my own laws. If we have robots that is subjected to unexpected forces, my 3 laws, which have also priority, are that if an unexpected force happen, we need to detect it, identify it, and control it. Especially if we think that, I mean, in the context where there might be humans around. So that's the first rule. The second one is to avoid failure and to recover, subject to the previous one, because the safety is more important. And the third one is to try to achieve the task anyway, and that's like the least priority. But if we can achieve it, it means that we have completely rejected the disturbance. So for our case, I will talk about our robots which have no torque sensor. So I'll present like a couple of methods that suits our robots. I think they can extend to robots that have torque feedback quite easily, which could maybe even increase the performances. Yeah, for every step, for every law, there is like a different loop, I could say, like the detection, the control of the forces, the recovery, and the task achievement have their own control loops. I will not present full solutions for that. I don't think that exists yet. I will present some estimation method here for the detection and identification of the forces. Some estimation in the case of highly dynamic motion, and the closed loop control that allows to achieve the task subject to the disturbances. So for the first one, I want to talk about a paper that we did like a couple of years ago about experimental evaluation of simple estimators of humanoid robots. And the word simple was like really important in this paper because in that one we were mostly comparing kinematic estimators that uses IMU encoders, maybe contact information, but it stays at the kinematic level. But I have developed also a dynamics estimator, and I think this one is the one that I will talk about today. The thing is that this estimator with the complex dynamics was producing higher errors than simpler one, even if it was computationally more costly. So it's not like much higher, like just more millimeters, but yeah, the simplest one were giving like bigger, smaller errors in the kinematics estimation. So yeah, that's not. I'm not happy about that, but I think I can improve it. But it's not the point. What I want to present is I still would promote it even if it were the case, because being accurate or precise is not enough to guarantee the quality of the closed loop control, especially in nonlinear dynamics. In linear dynamics, we have the separation principle where we could separate the estimation and the control. In nonlinear control, you need to deal with closed loop dynamics, which is not necessarily stable, even if the estimation and control are stable independently. So yeah, more properties like stability and smoothness, and maybe not being too sensitive to errors that are necessary to guarantee the quality of closed loop control. Also, with the kind of kinematic estimators that we have here, we usually build different estimations and that are inconsistent. So we have estimations of the forces, we have estimation of the kinematics, we have sometimes estimation of the absolute position during using SLAM, and they are not consistent each with other. And actually, they are living in different control loops. Sometimes the kinematics corrects for SLAM, but I haven't seen many times that SLAM correcting the kinematics. And I think that's something that's weird because we have just one single system, so we should have one single state. So that means that we have to refine the model and to be able to rebuild the same state, given all the measurements that we are having. And the last point, which is the most important in this talk, is that some variables are only observable with a rich model. So here I present the estimator that I developed through several publications. And so it's one state estimator, single state estimator that takes all the available measurements on our robot and builds floating base kinematics. And it gives also contact force information if they are not available with force sensor. We have even shown that we can stabilize the robot using this feedback without the force sensors. And in 2018, I have shown that we can get also other external forces that are not measured, that are not modeled, that are not contact forces. So the idea, I mean, the experiment was to ask the robot to perform a task with its hand. So its hand has a force sensor, but we don't use it. So we just ask this estimator to get the estimation of the forces, and we use the force sensor of the hand as a ground truth. And you can see that we are able to rebuild the forces and the moments of this contact, this external force, rather accurately, especially in the forces, maybe a little bit less in the moment, just using the IMU, the force sensor at the ankles, and the encoders. And here we show that we can even build an axis that goes not, I mean, I can rebuild the axis that is the closest to the contact, given these measurements. And this axis goes like 7 centimeters, has 7 centimeters of error between the contact point and this estimation. So we can get also information on the application point using this estimator. Of course, it is limited because it will only give you the force of one contact, I mean the resulting external force. So if you have 2 contacts or 2 forces, it will not be able to distinguish them. But the point is, we can simply see it as transforming the whole robot into a giant force torque sensor. And this is possible thanks to a model-rich estimator that is able to not only use the redundancy that lies between the force sensors and the kinematics, because the force sensors will give the forces and the forces will give the accelerations of the center of mass. So there is redundancy between the force sensor and the kinematic. Not only it deals with that, but also it's able to have new observable states thanks to this coupling. So yeah, this work is being extended. So it's been a couple of years that I haven't worked on it, but I think that we can improve it with more efficient implementation, better integration with absolute position and torque sensors, odometry, etc. But I think you would be right by saying that the precision is important. Actually, I'm not saying it's not important. So precision is important. And in the case of our observer, it relies a lot. I mean, the observer relies a lot on the dynamic model. So if the model is wrong, and the precision will be lower, and the modeling error will show up more in dynamic motions. So I think that's right. So that's why I will present another kind of estimation framework for the case of dynamic motion. And I put it here because that's usually the context where we need to avoid failure, at least for humanoid robot, where we need to recover balance. This is another estimator. So it's the idea is to consider, just let's suppose we know what is the fixed point of the robot. With the fixed point, the instant fixed point is at each instant what point of the robot, or even not really in the robot, could be like between the feet, what point in the frame of the robot is not moving, it has zero velocity. So usually it's around the contact points. We can consider, for example, the ZMP. So ZMP could be considered as the fixed point. If we know the fixed point, so just using the IMU, the encoders, and the joint velocity, we can rebuild the linear velocity in the world frame expressed in the local frame. So let me call it x1. And let me call x2 the direction of the gravity in the local frame. So this is this gives a kind of roll pitch, like 2 degrees of freedom of the orientation. So the state dynamics is actually really simple. So S here is just the skew symmetric operator. So that's just the cross product. And I would define like a really simple state observer, that this is like 6 lines here, like six rows, like 3 rows, that are 3D vectors. So in code is just like 2 lines of code, these 2 lines of code. And with this estimator, let's build just the vector of error. And the vector of error has dynamics that looks a little bit complex, but if I change the variable by looking at the error in the global frame, I end up with this dynamics. So this dynamics is linear. So these are 3D vectors too. These are errors. So when it's 0, it means that we have a correct estimation. It's stable. So it's globally exponentially stable. It means it will go to 0. But what is important here is to see that it is autonomous. It means that it doesn't have any input. It only depends on the state, on the error itself. It means the error dynamics would be the same whatever the motion of the IMU. Whatever the IMU is doing, the estimation will converge in the same way to the correct one. So it could be any kind of dynamic motion, any kind of impact motion. So for example, here in simulation, we just make the robot, we make this robot, simulated robot, here oscillate, then we make it somewhere around here, we make it fall, and we follow like the vector of gravity in the local frame. So here we can see the fall. Here also we can see the fall. So X and Z component are showing the fall. Here there is like a big impact. And here I compare several estimators. So the one that I presented here is this one, the red. And we see that the error is actually really, really small. And during the fall, it doesn't increase a lot. I mean, it's maybe the same order of magnitude as the error during the oscillation. So this is because the fall was respecting the hypothesis that there is a fixed point that we know. So we just use the force sensor to get the ZMP, and with the ZMP we can rebuild the position of the fixed point. So of course it depends on this assumption. So if I don't know the fixed point, or if it's wrong, or if the robot is slipping, it would be less precise, but the error would be filtered because this estimation is going through a complementary filter. So if there is like a short slip, it will be filtered. And anyway, that's better than the other estimators that just consider fixed points or use the forces to predict slipping, just to decrease the confidence that they have in the contact points. So yeah, we didn't make our robots fall, so we just I just show like some results in closed loop with this estimator. I mean, of course, it would work with it would work without issues. So in summary, so we just assume that there is a fixed point that allows to give us the linear velocity. Better noise filtering is obtained through this estimator. We have proven Lyapunov convergence, and to my knowledge, this is the only estimator that has proven Lyapunov convergence in humanoid robots. There are other estimators which have local convergence. This is a global convergence, so it's really strong guarantee, and the error is autonomous. So we are presenting also into a transactional automatic control a generalization of this estimator to the nth order filtering. That's filtering. Which can increase the rejection of noise. So that's submitted currently. So now let's move to the third law, which is to try to investigate how we can achieve the task in the presence of these unexpected forces. So throughout several publications, we have presented the torque control approach that uses robots without torque feedback. So one key idea is to, so this is the reference acceleration coming from the QP. And we integrate it and get the error in velocity between the integral of this reference acceleration and the current velocity obtained from the robot. And this integral term allows us to correct for errors in the sorry, errors in the just computed torque. So since we don't have torque feedback, we don't know what's the amount of friction. We don't know what's if the torque is actually achieved by the motors. So we correct it using this integral term. But it has even, I think it has interests even for torque feedback robots, because this kind of integral feedback gives a strong proof of convergence of the joint position. So S is the error in velocity. We know that S goes to zero exponentially. But since S is computed through the reference acceleration that takes into account the position and the velocity, we can prove that this amounts at having the convergence of the integral of the joint position error. So it's not only the position error going to zero, but its integral is going to zero. And that's yeah, that's known to produce a bigger, I mean, higher robustness, and to give no static error, even in the case of modeling error in mass distribution or this kind of stuff. This is really strong. So the guarantee that the integral of the joint position error goes to zero is strong, especially in the case that we are dealing with here, in the case where we have disturbances. So do we really want that? Actually, what we want is the convergence of one maybe specific or several specific tasks. And we have to acknowledge that integral terms can be dangerous. For example, if the robot hits the wall and there is like integral term, it would just try to break the wall. So we have submitted to IROS a series of safety measures, some anti-windup that is based on a QP that guarantees that the integral term will never exceed the given values. and it does it in an optimal way. So it doesn't. It only reduces the torque that is exceeding the value, but doesn't decrease the performances of other components of the motion. We have presented also some leaky integration scheme with the second order filter that allows to target specifically some kind of disturbances. So instead of using just simple integration, we can have a quick integration for stiction and really impulsive disturbances, and the slow integration that can deal with the modeling error. And finally, we presented the null space compliance that I will present here briefly. So the guarantees of convergence of the task can be improved just by changing a little bit the integral term. So instead of having just the integral term like this, we add also some terms that are related to the specific task that we want to achieve. So by doing that, we can guarantee the convergence of the integral of the acceleration error of the task. But similarly, since this comes from the QP, so the QP is aware of what is the desired one. So it means that we have the convergence of the integral of the task error itself. So for example, if I want, so if I want a 6D pose task, so the integral of the 6D pose error would be going to 0. And so that's really the same kind of proof of guarantees of convergence, but only on the tasks. So this allows us to make the remaining degrees of freedom compliant. So this is how we can demonstrate it. So this is our robot HRP5P, which has no torque feedback. So here it's on a stand. So the stand is not perfectly rigid. So when I say the hand is stiff, but actually you see it going down and up, it's mostly the stand that's moving. So here we are not, since we are applying really strong forces on the robot, we are not dealing with balance. We are just dealing with the task itself. So we put the robot on the stand. So here the task is really stiff, and also the null space is stiff. So if I activate the null space compliance, I have the same property, like it's the same stiffness for the task. But now the null space of the task now is compliant. It's not really easy to move it, because this is a passive compliance, so I still have to deal with the friction. And it's a really high gear ratio robot. It's a really powerful robot. But what I want to show is that I can move degrees of freedom, and at the same time, the hand remains in place, even if I move the other degrees of freedom. So here the arm has 9 DOFs, and the task is 6 DOF. So I have 3 DOFs of null space, but only 2 are easy to move. The third one is really complicated because we have a high friction and we don't have big leverage arm. And actually, we can also have fun and combine this with some admittance. So now we can have at the same time different compliance, either in the task space or in the null space. So here I can move the null space, and this remains in place, or I move the end effector itself, and it follows. So yeah, we can have fun and combine several kinds of controls. And so this this can be also used for. So this is like really recent result that we got. It's not even in the submission to IROS. We can use it for moving. So we can, like, the robot is asked here to perform some trajectory in the space, but there is like there are vertical bars. So the robot is not aware of the bars. It has no measurement of the bars. It's completely blind, and it has no feedback of the presence of the bars, even if it touches them. But still, the robot is asked to do it, so it collides completely with the bars. But thanks to the compliance, it's able to reach the task. So it's not perfect, of course, because during the disturbance, the task error increases. But thanks to our control, we know that this task error will go back to zero quickly. So I can show you also the trajectories here. So this is the reference trajectory that is required here from the robot in the space. So this is x, z, and this is x, y, z, sorry, and this is x, z. Maybe here it's clearer. So this is x, y, z reference in blue, and the actual position in red. And we can see that, yeah, there is some errors here that happen just because of the disturbance, but the impact was compensated here, and the task could be achieved. And more importantly, we didn't break the robot, we didn't break the environment. And with this kind of robots, especially a Sharpie-5P, this is completely impossible with position control, except if we modify it in a really extensive way. So, sorry. So that's basically the methods I wanted to present. Of course, the control parts are a little bit missing in my presentations. We have been working on them in a few works. So here you can see work by Rafael Cisneros Lemon, where the robot in simulation hits the environment, but it's still able to keep balance and to reject it. And with Masaki Muraoka, we are working on how to integrate. Oh, that's a mistake. How to use a measurement of how to say, if we can measure the error between the desired and the real forces, how can we include these measurement into the stabilization? So here there is different friction ratios between these areas, but there is a force sensor at the wrist, so we are using actively this data to correct for the stabilization. This has also results on the real robot, but yeah, so the paper is submitted in RAL, so if, I think it's about to be accepted to RAL. So yeah, please check it if you want to have more details. So thank you very much. I'm sorry for this maybe a short presentation, but yeah, that's it. There are still many missing bricks to achieve these laws, and yeah, I would be happy to discuss that with you.
So Mehdi, thank you very much for being with us despite the sickness. Hope you can recover soon.
Thank you.
Yes, the presentation is very impressive. I do learn a lot of missing details. I'm wondering that are there any questions from the audience? Well, if no one is willing to grab this opportunity, may I ask one point, Mehdi?
Yes, please.
Yes. So basically, I'm wondering that is it possible? I mean, according to your three levels of laws, I'm mostly working on the first level, that is detect, identify, and control the external forces. So I'm wondering that is it possible to estimate the external force without using a force log sensor? I mean, only using encoders and IMUs.
Using only
encoders
and IMUs.
Yes.
Are you talking about humanoid robots?
Yes, because I noticed that some small size toy robots, they can kind of react to the external disturbance and perform kind of push recovery. So yes. I'm wondering that is it possible for humanoid to estimate external force using only encoders and IMUs?
So in the thank you very much. That's a really good question. So in the paper here ICRA 2018, I have presented also the case if there was no force sensor. So if there was an estimation, but it wasn't really good. The how to say, the force component was not really good, because with the IMUs it's not possible to get like you cannot get all the components of the external force. You can get moments that can deform the robot. So you mostly get 3 DOFs out of the 6 DOFs of the forces. So it is possible, but the quality is much lower. I don't know if I have here the results. I think I have them here. Where is it? So with the same experiment, can you see the paper?
Oh, yes.
So the same experiment, I also tried without the force sensors. Where is it? Yeah. So here we can get the force, 1 force and 2 moments. That's what I could get.
Okay. Yes. Great. Thank you for the answer. I will check the details in the paper in the future.
Yeah, please. And if you have questions, don't hesitate.
Yes. Maybe one more point is that you mentioned that the dynamics approach can produce bigger errors. So what could you, I mean, could you please briefly answer why is that? Where does uncertainty come from? Does it come from the uncertain dynamics model, or?
So for that specific experiment, I know that the IMU had the gyro had some bias. So this allowed me to make my model more complex and to add the bias estimation, but this hasn't been released yet. So yeah, so what happens usually if I find a big error, it means that the model is wrong and it needs to be refined. So I think it's interesting also because it allows to have a nicer model, and the nicer model is a better predictor of the dynamics of the robot. So I have been using the models for estimation also for the control, and we have shown that the prediction is not that bad if you refine your model.
Okay. So we can maybe one of the possibility contributes from the uncertain models.
Yeah. So yeah, there is the uncertainty in the contact model is the biggest one. So I worked a lot on that, but there is still some modeling errors that need to be tackled.
Okay. So if there are no more questions from the audience, I would like to thank Mehdi again for the nice presentation and the excellent experiments, and hope you can recover soon.
Thank you very much. Bye.
Bye. Okay. So our next speaker will be Xu Ruoyu from Chinese University, Hong Kong, Shenzhen. This is a teaser session. Basically, Ruoyu is going to present a predictive control framework for manipulator on a disturbed seaborne platform. Ruoyu, could you hear me?
Yeah, I can hear you. I can hear you. Thank you, okay. Dr. Wang.
I can see your screen.
Yeah. Okay. So shall we start?
Yes, please.
Okay.
Please go ahead.
Hello, everybody. Today I'm going to present a predictive control framework for manipulator on a disturbed seaborne platform. As we can see in these 2 videos, it's a challenge for UAV to land on a disturbed platform. And it is more difficult to land a UAV on a small surface vehicle because a surface vehicle is more unstable. So we are going to use manipulator to help the UAV land safely and accurately. This is an experiment to catch the UAV on a disturbed platform. And the manipulator is mounted on a rotary platform whose motion is 0.16 Hertz and the amplitude is 10 degrees. The position of the UAV is measured by the motion capture system, and the manipulator is controlled by a Jacobian transpose method. And the end effector of the manipulator is designed to tracking the objective by a proportional controller. We can see that the response of the manipulator is very slow. And after about 3 tries, at last it will catch the UAV successfully. But if we increase the frequency of the base motion to about 0.48 Hertz, we can see that it will be very hard to control the motion of the manipulator. Recently, more and more research shows that MPC has a good tracking performance. So to stabilize the end effector motion, we proposed an MPC controller. The control framework consists of 3 parts. In the gray box here, it's a high-level controller. The trajectory is generated here by the predicted USB motion. And the yellow box is the MPC controller. The model in MPC takes the delay of each joint controller into account, and the parameters in the MPC is updated in real time by an uncertainty observer. The MPC will feed the velocity command to the low-level joint velocity controller in the blue box. And what in the right side is the simulated USB motion based on the collected data from level 1C condition. In this framework, firstly, the roll and the pitch of the USB are predicted in real time. And the black line is collected data from a real USB, and the blue lines are the predicted motion. We can see that the predicted motion is agree with the real motion, which will be further used to generate the reference trajectory for the MPC controller. The dynamic of each joint is estimated by a first-order delay model. That's exactly what we mentioned in just before. And this is the model. The TM is the time constant, which will be observed by an uncertainty observer, and it will also be updated in real time. The model predictive controller is formulated based on this model. To verify the feasibility of our method, we did a simulation, and this is the result of the simulation. On the left side is the platform before stabilized, and on the right side is the platform stabilized by our method. We can see that our method works. We also compared our method with an inverse kinematics controller. And in this simulation, we let the manipulator tracking a circle in a inertia frame, and at the same time, the base is fluctuating. The motion of the base is generated by the USB motion collected from at sea. And according to this simulation, we can find that our method has a better tracking performance compared with traditional method. Our future work is to implement this method to a real manipulator. Thanks for your attention. That's all.
Thank you, Roy, for your presentation. I think indeed this is a different flavor compared to other presentations where mostly humanoid robot or other under-actuated robots are presented. I'm wondering that is there any questions from the audience? Okay, so if not, Roy, thank you again for your presentation. And our morning session will close a little bit ahead of time. So we will meet again. Thank everyone for joining us for the great presentations, and we will resume the Zoom meeting again in the afternoon.
Thank you.
So take care and see you later.